Welcome to section 2 of chapter 7, inverse functions and relations. I want to remind you that your note sheet should look exactly like mine. You should have made the same notes, the same highlights, and the same work as I have done. We're going to look at inverse relations first. A relation is just a set of points. When we talk about an inverse relation, what we're doing is we're taking a given set of points and we're reversing the order of the x and y coordinate. So we're given this initial relation, and we're going to take each point and we're just going to reverse the coordinates. So instead of 1, 2, we're going to have 2, 1. Instead of 3, 4, we're going to have 4, 3. And instead of negative 5, 6, we're going to have 6, negative 5. And since the values in the x and y positions have switched, the second set we can call the inverse of the first set. Another thing that I want you to notice is if you graph these points and the inverse of the point. So I'm going to first graph the point 1, 2. If I graph the inverse of 1, 2, it was 2, 1, which is right here. So these 2 points are reflected across a line. And you'll notice that this happens for every single point in the relation. If I graph the point 3, 4, and then 4, 3, so 3, 4 is up here, they're both reflected. So that's kind of how these two connect. Okay, so that's going to be something that you'll always want to double check whenever you find the inverse relation, is that it's reflected across the line y equals x. And that is how you find inverse relations. I want you to try the next example on your own. So go ahead and pause and resume once you have finished. Go ahead and check your answers at this point. Again, all I did was I took 6 and 5 and I switched them. If it was negative, I kept the negative. So instead of negative 4, negative 10, it's negative 10, negative 4. It's the same way for this. If we had a point, any point AB, it would just be BA, would be the inverse relation. So an inverse relation was a set of points. An inverse function tells us that this is going to be continuous. We use certain notations to show that this is an inverse function. The notation that we use is written here. I want you to make sure that you do copy this. And this is read as the inverse of f. It is not read f negative 1x. It's not read anything else besides the inverse of f. Suppose that two functions are inverse functions. If this is the case, if we know that they are inverse functions, the graphs are reflected over the line y equals x, just like the relations were on the previous example. And you'll see what I mean when we start graphing these. This is going to be a great reference slide to always go back to. This tells us how we're going to find an inverse function. So what we're going to be given is they're going to give us a function, and they're going to ask us to find the inverse. So this function can look like anything, but it's always going to be written as f of x equals something with x's. So this could be an example of a function. What you're going to do with this function is you're going to follow these steps in order to find the inverse function. So we're going to do a couple examples together, a couple on your own, and you're going to see how this works and what happens when it does. So like I said previously, we are given a function. F of x denotes this function, and we're going to follow the steps. So the first thing we're going to do is we're going to replace f of x with y in the original equation and just rewrite it. Notice that's the only thing that I've done thus far. Next step is to switch x and y. So here was where my y and x were, and now x and y are in each other's spots. Now we use algebra to solve for y. We're going to multiply both sides by 2. And end up with 2x equals y plus 6. And subtracting 6 gives us our solution. We're not quite done yet. Right now we just have y equals. So our final step is instead of y, we are going to write this inverse of x. And here it was y equals this piece. So now it's inverse of x equals that piece. I want you to do the next example on your own, following the same steps in the same format. When you've finished, go ahead and check with my solutions. Go ahead and check mine. One of the more important things that people often forget is this last part, writing f of -1 of x, or the inverse of f, is equal to the solution. If you are given two functions and you're asked to verify if they're inverses, we have a couple different routes we can go. The first one is this definition that they give in the book. It says if you're given two functions, f and g, and their compositions are both equal to the identity function. The identity function is x. Here's the first composition, f of g of x, and the second, g of f of x. If, when you find both these composition functions using the given functions, if you get them both equal to x, then these are inverses. The other way that I would encourage you to use is if they give you two functions, then take the inverse of the first one and see if that inverse matches the second function, because you know how to find inverse functions, so use what you know in that aspect. I'm going to show you how to do it both ways. The first thing I want you to do is change this problem to 5x plus 10 instead of 5x minus 2. We're just going to change the problem for convenience to show us what this is going to look like. I'm going to use the first method to show you how to verify that two functions are the inverse. So the first thing I want to do is I want to find what f of g is. The next thing I want to find is what g of f of x is. At this point, you know g of x is right over here. So what I'm going to do is I'm going to take that and plug it in because I know that for a fact. And now I'm going to take this chunk of information and plug it in for every x in the f function, giving this. After distributing, I get that this composition function is x. I have to verify that the second composition function is also x, which I will do now. Start by plugging my f of x function in. And now I will take this information, this chunk, and I will plug it in for every x in my g function. And when I do, I get this, and I simplify it and reduce, and I end up with x. So now that I've confirmed that both our composition functions are equal to x, I know that they are inverses. The second way that I would show to do this is if I was given these two functions, I would look at the first one, or the more easy one to look at, and I would find the inverse of this function. So I'm going to find the inverse of f of x. After finding the inverse and simplifying, so here what I did was I put this right here, and this simplified down. Once I found it, I found that this inverse of x was the exact same as my g of x function. If I find that, then I know that these two are inverse functions, and I don't really have to mess with the compositions. This is giving you options on which ways you want to verify that they are inverses. Anytime you graph an inverse function, it will always be reflected over the line y equals x. So what I want you to do is when you find the inverse, I want you to graph all three. So I want you to graph the original, I want you to graph the inverse, and I also want you to graph the line y equals x. You will see that these lines are reflected over y equals x. If they are not, if points do not reflect across, then you've found the inverse function incorrectly, and you'll need to go back and double check this to ensure that you have the correct solution. We will talk more about this graphs in class. But the main thing to remember from this page is that you want to graph the original function, the inverse, and y equals x in order to verify that they are inverses. One-to-one is another way that we can classify a function. In order to classify a function as one-to-one, we have to find the inverse function and see if the inverse is also a function. If the inverse is a function, meaning it passes the vertical line test, then the original function is said to be one-to-one. So in order to verify these, you'll want to look at the graphs. It'll be your easiest way, and you'll also be able to just say very quickly, is it one-to-one, is it not one-to-one, by looking at the graph of the inverse of the function. I'm not even going to really worry about the graph of the function because I know it's a function, but if I get an inverse graph that looks like this, that would make it 1-to-1 because it passes the vertical line test. If I got an inverse function that looked like this would also make the original 1-to-1. So again, I'm just finding the inverse, I'm graphing the inverse to see if it's a function. And if it passes the vertical line test, it is a function. If I graphed the inverse and it was like this, it fails the vertical line test. It hits here and here. This is not a function. So if the inverse is not a function, it's not 1-to-1. In order to be 1-to-1, the graph of the inverse must also be a function.